This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss a specific concept associated with the 2019 AP Calculus exam, free response question AB3 BC3, namely properties of definite integrals. My name is Steve Kokoska. I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start with a quick review of the definition of the definite integral, and mention a few issues for you to think about. For example, what happens if the lower bound in a definite integral is greater than the upper bound? The typical properties of the definite integral usually follow this definition, and before any techniques of integration. So I'll introduce 4 of these properties, consider some interpretations, and present some examples. And then I'll introduce 4 additional properties and more interpretations, and finish with an example. In many AP Calculus courses, the properties of definite integrals are introduced right after the strict definition of the definite integral. In fact, many of these properties can be proved by using this definition. So let's follow this presentation structure and begin with a little bit of background information. Consider a limit of this form. Now, we've seen limits of this type when we try to compute the area of a plane region. And this same type of limit occurs in a wide variety of applications. For example, finding the distance traveled by an object, the length of a curve, or the volume of a solid. This limit is so important that it has a special name and notation. Here's the formal definition of the definite integral. If f is a function defined on the closed interval a to b, let's let p be a partition of the interval a to b, defined in the following way. Choose sample points x sub I star in each subinterval, and let delta x sub I be the length of the ith subinterval. Then the definite integral of f from a to b is defined to be this limit, provided that it exists, and gives the same value for all possible choices of sample points. If the limit does exist, we say that f is integrable on the interval a to b. Let's take a closer look at this definition. The precise meaning of the limit that defines the definite integral involves an epsilon delta type argument involving epsilon and n. It starts, for every epsilon greater than 0, there exists an integer n. Now, I'm not going to discuss this in detail, but I think you should be aware of this strict definition. Another way to define the definite integral involves the norm of the partition. The norm of a partition is the largest value from among the delta x sub i's. And here's what the definition looks like involving the norm of p. And just to make sure that we agree on the terminology associated with the definite integral, the function f of x is called the integrand. The values a and b are the limits of integration. A is the lower limit and b is the upper limit. And the simple dx indicates the independent variable is x. Remember that the definite integral represents a number, and that value, that number, does not depend upon the dummy variable. So each of these definite integrals represents the same number. And finally, this sum is called a Riemann sum. So the definite integral is the limit of a Riemann sum, and an integrable function can be approximated to within any desired degree of accuracy by a Riemann sum. The definite integral is defined for an integrable function, but not all functions are integrable. This next theorem shows us the most commonly occurring functions that are, in fact, integrable. It says if f is continuous on a closed interval a to b, or if f has a finite number of jump discontinuities, then f is integrable on that interval ab. That is, the definite integral from a to b of f of x dx exists. Now, consider this example. This figure shows the graph of a function f. How would you find the value of this definite integral? And I'll leave that for you to think about and explain. So, how do we evaluate a definite integral, for now, without any anti-differentiation rules? Well, we have to use the definition, and that means we have to find the limit of a Riemann sum. If f is integrable, then the limit definition returns the same value no matter how we choose the points x sub I star. So we often simplify calculation, again for now, by taking the right endpoints of each subinterval, for example, with equal subintervals, that is a regular partition. Now another method is to interpret the definite integral in terms of area. And in fact, free response question AB3 BC3 involved this concept. Here are just a couple of additional notes associated with the definition of the definite integral. In the definition, we assumed that a is less than b. However, this definition as a limit of a Riemann sum still makes sense, even if a is greater than b. For a regular partition, we can write delta x like this, and therefore the definite integral from b to a of f of x dx is equal to minus the definite integral from a to b of f of x dx. And finally, if a equals b, then delta x is equal to 0, and the definite integral from a to a of f of x dx is equal to 0. And this is proved from the definition. So finally, here are some properties of the definite integral. The definite integral of a constant c from a to b is c times the difference b minus a. The definite integral of f plus g is the definite integral of f plus the definite integral of g. If c is any constant, then the definite integral of c times f of x is c times the definite integral of f of x. And the definite integral of f minus g is the definite integral of f minus the definite integral of g. Here's a closer look at these properties. Property 1 says that the definite integral of a constant function, f of x equals c, is the constant times the length of the interval. If c is greater than 0 and a is less than b, then c times b minus a is the area of the rectangle bounded above by the graph of y equal f of x equals c, below by the x-axis, on the left by x equal a, and on the right by x equal b. In words, property 2 says that the definite integral of a sum is the sum of the definite integrals. For positive functions, this integral can be interpreted as the area under the graph of f plus g is the area under f plus the area under g. And this figure illustrates this concept. This property is proved using the definition of the definite integral and the fact that the limit of a sum is the sum of the limits. Property 3 says that the definite integral of a constant times a function is the constant times the definite integral of the function. My favorite way to think about this is that constants pass freely through definite integral signs. And this property can be proved using the definition of the definite integral and properties of sums. Property 4 is proved by writing f minus g as f plus a minus g. And then we can use properties 2 and 3 with c equal to minus 1. In words, the definite integral of a difference is the difference of the corresponding definite integrals. Here's a typical example involving these 4 properties. For the constants a and b, let's suppose that these 2 special definite integrals can be evaluated by using these formulas. Use the properties of definite integrals to evaluate each of the following. I'll solve part A, but I'm going to leave the rest for you. And remember, at this point in the course, we're solving these problems without any anti-differentiation rules. We're just using the properties of definite integrals, and perhaps even the definition. First, we can rewrite the definite integral using property 2. The definite integral of a sum is the sum of the definite integrals. Then the constant 2 passes freely through the definite integral symbol. That's property 3. In the next step, I used one of the given evaluation formulas and property 1, evaluation of the limit of a constant. And finally, I chose to simplify to get a final answer of 25. Property 5 involving definite integrals shows how to combine definite integrals of the same function over adjacent intervals. This concept was used in the solution to free response question AB3 BC3. Suppose that all of the following definite integrals exist. Then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. There is a very reasonable geometric interpretation of this property if f of x is greater than or equal to 0 and c is between a and b. In this figure, the area under the graph of f from a to c plus the area from c to b is equal to the total area under the graph of f from a to b. Here's an example that involves this property of definite integrals. Suppose we're given the value of these two definite integrals. Find the integral from 7 to 10 of f of x dx. Use property 5 to write the definite integral from 0 to 10 of f of x dx with c equal to 7 between a equals 0 and b equals 10. Then simply solve for the unknown definite integral. And here, the definite integral from 7 to 10 of f of x dx is equal to 10. Here are a few more properties of definite integrals, and all of these involve comparisons. Let's suppose the following definite integrals exist, and a is less than or equal to b. If f is greater than or equal to 0, then the definite integral of f is also greater than or equal to 0. If f is greater than or equal to g, then the definite integral of f is greater than or equal to the definite integral of g. And if we can bound f above and below, then we can also bound the definite integral from a to b of f of x dx. Here's a closer look at these three properties. In property 6, if f is greater than or equal to 0, then the definite integral represents the area of the region bounded above by the graph y equal f of x, below by the x-axis, and lying between the lines x equal a and x equal b. So the geometric interpretation of property 6 is that areas are non-negative. Property 7 says that a larger function has a larger definite integral. And this follows from properties 6 and 4, and because f minus g is greater than or equal to 0. And property 8 is illustrated in this figure. If f is continuous, take small m and capital M to be the absolute minimum and maximum values of f on the closed interval a to b. In this case, property 8 says that the area under the graph of f is greater than the area of the rectangle with height small m and width b minus a, and less than the area of the rectangle with the same width and height capital M. Here's one more example that makes use of these comparison properties. Use property 8 to estimate this definite integral. Now, I claim that f of x equal 2 to the minus x squared is decreasing on the interval 0 to 1. Now, you might have to think a little bit about how to justify this. If that's true, then the absolute maximum value of f over the closed interval 0 to 1 is at the left endpoint, and the absolute minimum value is at the right endpoint. So I can use property 8 and a little simplification, and I can bound this definite integral between 0.5 and 1. I used a little technology to illustrate and confirm this inequality. Using the TI-Nspire, I defined the function f, and then I found the definite integral on a calculator page. Notice that my answer is a numerical approximation, approximately 0.81. This value is between 0.5 and 1, thank goodness. I wonder if you can explain to me why I didn't get a symbolic answer. And here's a visualization of this result. You can see the two rectangles in here and the area associated with all three regions. And this also helps to confirm the inequality. I hope this video provides some insight into the basic properties of definite integrals, a few AP Calculus type problems, and the use of technology to solve and visualize these types of problems. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.